Okay, this video is 2.1.2. We got two objectives. One, we're looking at introduction to function notation and how we can handle multiple equations as functions, and also looking at intersection of these functions. So those are the two things. So let's first talk about a scenario where we have several people. Let's say we have Sue, Pete, and Bob. Okay, and we're going to define how much money they make. Okay, so Y is going to tell us how much money they make. Oops, sorry, getting out of control there. And X is the input of how they make. Okay, so that's the input, and that is basically based on how many hours of work. Sorry, how many hours of work they put in. Okay, so let's say Sue makes um, $10 an hour. Okay, where Peter makes not as much an hour, $5 an hour, but he gets paid $20 just for showing up. So he gets $20 plus time after that. Okay. Then Bob, he gets paid, um, let's say this a flat fee for showing up, right? So he pays $1 an hour, but he gets $100 a day for showing up, and then $100 for every hour. Okay. So obviously they all are based on the number of hours of work. Okay. But notice we have different equations, and we have really the outputs are different because they all get differently. So one way we could distinguish this is we could put their names here. Okay, so Sue, Peter, Y of Peter, Y of Bob, and so forth. Okay, so what we do now is we say, okay, instead of like letters simplifying numbers, we now can have letters simplify entire functions. So I'm going to rewrite this whole equation, and I'm going to tag it function S for Sue. I'm going to tag this whole equation as equation or function P for Peter. And I'm going to tag this one as function B for Bob. So now those letters represent the entire equation of how much they work. Now to do function notation, we say, okay, this function is based on a certain input. So we're going to say S of X. So this is just really this notation. This is kind of how we write it. So we say, okay, the function of Sue, the function S, is based on X, how many hours you work, and that equation is 10X. The equation for Peter then is 5X plus 20. And for Bob, it's 1X plus 20, or 1X plus 100, okay? So we give the names, the functions, different names. So this is called function notation. This is what we're working on here today. Okay. Now, let's say I want to figure out how much Sue and Peter made together. Okay. And each day is different, but I want to say, okay, just tell me, each day, at the end of each day, how can I figure out how much you make together? So to do that, we'd say, okay, we just simply add Sue's money plus Peter's money. So we could do that. Instead of adding single numbers, we can add whole equations. I'm going to add the function of Sue's money plus the function of Peter's money. And if we did that, we could simply say, okay, takes Sue's money plus Peter's money Sorry, my pen's a little slow here. That's supposed to be a 20. And we just combine like terms. We say, okay, the product of those two is, okay, together they make $15 an hour. And it's combining like terms, and they start off with 20 bucks. Okay, now if I said I want to then find how much more Bob makes than, let's say, Sue, we could then subtract them. So we can say Bob's equation is 1x plus 100. Take that function and subtract Sue's function, which is 10x. Okay. And again, how would I write it mathematically? It's going to look like this. Function of b of x minus s of x. Bob of x minus Sue of x. Okay. You notice we combine these like terms, we get negative 9x because the x's are there, plus 10. Okay. So again, he starts off with more, but over time he starts to lose more money. Bob does because he's not making much an hourly. So these are like sum equations. Here we add them up, here we find a difference, okay? So to show you that we can treat letters and functions the same way like we just did variables before. So let's kind of take a look at a scenario here. So here we have a problem. And notice instead of using y, we call each equation f of x. So that's like the equivalent of y. And that's the equivalent of y too. So, this axis is the output. So this axis is, the f of x and is the g of x. In all essence, it's the y, but it's the y for each different person. Okay. So let's go ahead and graph these. I'll graph the f in red. So I'm going to start at 1, and we have a slope of 1/2. So I'm just going to put that on the graph. It's a linear function, arrows at both ends, continuous. And do this one in black. So I'm going to start at 9. We have a negative slope. And come down. And the main key objective of this is, okay, where are the two lines equivalent to each other? Where did it equal? Where did they have the same input and the same output? So the question is, where is f of x, that equation, equal to g of x? Now notice they're both based on x's. So that's why the x's have to be the same, and then the outputs have to be the same, okay, the dependent variable. So looking at this graph, where does it appear to happen? Right about here-ish, okay? So roughly when 3 is the input, then the output is roughly 3. So the way we do this, I'm going to test it. I'm going to take 3 and evaluate it into both equations. I'm going to take 3 and evaluate it, i.e. plug it into this equation. So this is how it looks like. I'm just going to write that down here. F, and the reason, instead of putting an X, we say we want to input 3 into that equation. Okay, sorry, my computer's going to die here in a little bit. So every time we see an X, we replace it with 3. Okay. Now we're going to take 3 and evaluate it. So that's 3/2 plus 1. So that'd be roughly 2.5, 2.5. Okay. So that's like an ordered pair. We could say the ordered pair 3, comma 2.5. We have an input and then we have an output. Okay. Then we could do the same thing for g of x. And instead of putting x there, sorry, we're going to put a 3. We're going to evaluate it. A little slow there. So -2, again, replace the x with a 3. So that's -6 plus 9. It is +3. So we can see that the values are pretty close. This one we got a 3. This one we got a 2.5. So this point, and they're very close. So we could say, the intersection is nearby or approximately that intersection. Okay. So if I also subtract it, let's say, get rid of this, so I have a little more room. If I want to subtract f of x minus g of x, find the difference, how far apart they are, okay? And at that point, I could do it like this. Just kind of watch my total station and say, when I plug 3 into both of them, and subtract it, well, that value was 2.5. This value was 3, and notice we have -0.5. Pretty close. A number pretty close to 0, meaning that we're pretty accurate. And that's kind of what we're doing. So this video, again, talking about function notation, and then also talking about intersections of graph.